Okay, I think probably we should start now. And for those people who join late, they can maybe watch the video later to catch up. And so it's my great pleasure to have to introduce Professor Lucia Gualtieri from Stanford Geophysics. Lucia got her bachelor and master's degree from the University of Bologna in Italy, and her PhD in geophysics from IPGP in France and the University of Bologna. Before joining Stanford as assistant professor last year, she was a postdoc fellow at Columbia University and Princeton University. Lucia's research focused on using seismic data and numerical simulation to understand environmental processes as well as the structure of the Earth. And Lucia was the winner of the Kitiaki Young Scientist Award by AGU in 2017, one of the highest honors for early career seismologists. And with this, let's welcome Lucia to give her talk titled Exploring Environmental Processes Through Seismological Observations and Numerical Modelings.
Thanks a lot, Jens, for this nice introduction, and thanks everyone for joining. Thanks for inviting me to give this virtual seminar. So today I'm going to discuss about how we can use seismology for studying environmental processes, with a special focus on the ocean and the signal that comes from the ocean that you can see already in this slide. So as a seismologist, we are interested in deploying seismometers on Earth and studying the ground motion of the Earth during earthquakes, but during also any other kind of forcing at the surface of the Earth. So this is the first global scale seismic network of seismometers in the 60s. Digital data was recorded by those seismic stations. And as you can see, those stations covered most of the land of the continents, but you see also a lot of gaps. So after years, basically we were able to go further and deploy seismometers with better quality data, and also all over the world, with some gaps, as you can see in the ocean still. There are regions of the Earth, like the US, where you have a very dense network of stations. This is a map of the EarthScope project US array, transportable array. And over a decade, basically those seismometers were moved all over the US and allowed to have this dense coverage. Situations like this can be seen, for example, in Japan, where you have the INET network of seismometers that cover all over the Japan. But as you can imagine, you have a lot of data coming from all those seismometers nowadays, and how this data looks like. So this data allow us basically to monitor in near real time the Earth. And here you can see a snapshot of a near real time seismic monitoring of earthquakes. You can go online and basically check when and where the last earthquake happened all over the world. So what we record is actually something like this. So we have here displacement as a function of time. And what you can see is that there is a major earthquake. You can see that it stands up from the big ground vibration. But as Gutenberg said in the 50s, you can also see that the ground is never at rest. You never see a flat seismogram. So basically, we record a lot of things other than earthquakes. And here you can see a couple of examples. So on the left, you see seismic record due to a tornado. This is a part of the transportable array, so the one I showed you before. And what happened in that case was that about 2 kilometers away, so pretty close, there was a tornado, and people were able to record the seismic signature of this tornado. You can see here the vertical amplitude of the ground and also the pressure associated with this moving atmospheric phenomena. On the right, you can see the signature of the sediment transport along a river. So we are here in Nepal, close to a major river. And you can see this is a spectrogram. So basically you have a frequency as a function of time. It's pretty small, but this is a year. And the color represents the power spectral density, so the power of the seismic records. What you can see is that you have a very strong patch during the summer months. You'll see the same when you look at the seismograms. So you see this black seismogram, which is in July, and this gray seismogram, this one was recorded in January. So during the summertime, and actually in that region is the monsoon season, what you record is a big increase close to a river of the background seismic vibration. And this is associated to the sediments that move along the riverbed and strikes the ground multiple times. In polar regions, you record other environmental processes called glacial earthquakes, so are calving generated events. So basically the ice breaks apart and generates seismic waves like those on the bottom of the screen, where you have the amplitude of the ground displacement as a function of time filtered in two different frequency bands. Those are particular earthquakes because you can see that, for example, they are strongly seasonal, this green histogram here, and they also increase over the number of those events increases over the years, which is a sign that those are not tectonic events and are likely related to phenomena that are associated to our changing climate. So other phenomena are mass wasting events that we can record. So landslides, like this one, and here you have the seismic signal associated with it, or a rockfall, and here you have the seismic signals. Here is another example. This occurred almost a year and a half ago now. So in December 2018, we had a huge tsunami going on in Indonesia, and for days, there been a debate if this was a tectonic classical earthquake or not. And what came out was that this signal was associated with a landslide that occurred at the Krakatoa volcano. So basically one flank of the volcano went down, struck the water and generate the tsunami. So those phenomena are pretty different than earthquake, and we can actually see that difference when we look at the seismic waves. This is an example of a rockfall, a landslide, and an earthquake filtered, so the signal are filtered in the same frequency band, and this is displacement as a function of time. And you can see that basically those are pretty different, especially at the beginning. For the earthquake, you have the body waves emerging, while you don't see anything for the rockfall and the landslide, and you see a gentle onset at the beginning of those events, landslide and rockfall. And studying those events with seismology ended up to be very useful, for example, to study what was the trajectory. Sometimes those events occur in very remote places. And so it is difficult to go there or even to observe the event when it happened. And so with seismology, as you can see in this figure, you can actually reconstruct the trajectory of the center of mass. You can compare it with the topography and see that we get a very good match. And you can even estimate the mass. For this specific landslide, this was a very big one. The mass was about 25 Great Pyramids of Giza. So really, really a big landslide. And as I said, you can distinguish between earthquakes and other events, also not just looking at the seismograph, but looking at the source. This is the amplitude, the normalized spectral amplitude for the three components of the force associated with the source of a landslide. And this is the equivalent for an earthquake. So what you can see is that at long period, you have a different fall off, which can allow us to distinguish between the different sources. So you have all those events which gives you some deterministic signals in the records. So you have a similar like earthquake signal showing up in the seismic records. But as Gutenberg said, the ground is never at rest. So basically, in absence of all those events and many more that occur at the surface of the Earth, you have a signal like this that goes on and on all the time and is omnipresent everywhere on Earth. This has been called historically by Gutenberg itself at the beginning of the 20th century microseismic, and has been then called noise in the years because basically for the people interested in earthquakes, this was really a disturbing signal. It was a noisy signal. But I hope to convince you by the end of this talk that this is actually not noise. We can turn this noise into a signal and study the environment. So why it is interesting to study this quasi-random vibration of the Earth? Well, the first motivation I want to give you is that really this signal is the major part of what we record on Earth. So we can have, as you can see in this plot here, which shows you a month of records. Each row here is 24 hours of record. You can see two major earthquakes, magnitude larger than 7. You may have smaller earthquakes hidden behind the background signal, but all the time you see there is these small vibrations going on. And if you see something like this, you see around October 11th, you know that your seismometer is broken. So we actually use this tiny small vibration to monitor that the stations are working. Basically computing the power spectral density, so moving from the time domain to the frequency domain, and plotting, for example, the power spectral density as here as a function of period. We can actually, doing this all over over time, we can actually monitor that the seismometer is actually working. Another motivation that is important to mention is that this is really a unique, I will go more into this in a moment, but this is a very unique data set because it is generated by the interaction between different systems of the Earth, and in this case is the ocean atmosphere and the solid Earth. So basically this signal carries the imprint of multiple systems and can allow us to monitor what happens in other systems like in the atmosphere using seismic waves. This is an example of what we can do. This is the tropical cyclone intensity for 3 events, 3 tropical cyclones as a function of time. The black curves are is the intensity observed through satellites, and the red ones are instead the related to the intensity that we can estimate using seismic waves. So you can see that we can get the first order approximation of what's going on in the atmosphere using seismic waves traveling in the Earth. Then this is important and has been listed as one of the great challenging for the future because allow us to study how those systems interact and how the energy exchange in between the atmosphere and the ocean, and then the ocean and the solid Earth. The third motivation I want to give you, my last motivation, is mostly solid Earth driven. So people have observed that using this quasi-random vibration and cross-correlating signals at 2 different stations, you can actually image the Earth structure. Doing this, repeating this for multiple pairs of stations, you can build maps like this. This is something similar to medical tomography, where you scan the body of a person using X-rays. You can scan the Earth using seismic waves. And this has been done for years now, for a few decades, using earthquakes. But adding this new data set, as you can see on the bottom here, can allow you to improve your images and add more details about the Earth structure. So this field of research has been basically exploding in the last few years, and you can see here an histogram showing the number of publications, the black histogram, since the beginning of the 20th century regarding ambient noise. seismology. And in gray, you have an histogram for the number of seismometers deployed on Earth. You see that starting from about 2004, when people first discovered that you could actually image the Earth structure with this, basically the rate at which we are publishing in seismology, in ambient noise seismology, is actually higher than the number of seismometers that we are deploying on Earth. So I'm going to discuss about three main topics today regarding ambient noise seismology, or as we should call it, the background seismic vibration of the Earth. So the first one is how this mechanism generates. The second one is how we can monitor the ocean and the atmosphere using seismology. And the third one is how we can model ambient noise as a first step towards using it for imaging the Earth structure, but using what we know about the physics of the generation of ambient noise. So let's start. As I said already, this vibration of the Earth is generated by the interaction between atmosphere, ocean, and solid Earth. And basically, this quasi-random vibration that seems random and chaotic signal can be seen as really a deterministic signal when you move from the time domain to the frequency domain. When you compute the power spectral density as a function of period, like here, this image is taken from the Geoscope network, where you can, the Geoscope website, where you can actually check for each station of the network what's going on in terms of ambient noise. What you can see here is a very peculiar shape for the spectrum. So each color is for a component of the seismic vibration of the ground. So blue is vertical, up and down movement, north, the red one is a north-south movement, and the green one is east-west movement of the ground. So this shape is peculiar because with differences in amplitude, you can actually retrieve the same shape all over the world. So the main features are a big peak around 7 seconds. This is called secondary microseismic. Then you have a small peak around 14 seconds called primary microseismic. And then you have a plateau, which is pretty small for, pretty low for the vertical component and higher for the horizontal component, which is called the seismic hem of the Earth, which occurs at longer periods. You have also a minimum around 1 Earth, 1 second, which seems also to be a global scale characteristics. So where those different parts of the spectrum are coming from? Well, a large part of it are coming from the ocean. So excluding the short period part in which you'll find activity from lakes, rivers, even human activities, and excluding the long period part where you have the atmospheric pressure directly having an effect on the ground, but you also find tides and so on. In the about 2 seconds, 300 seconds, this is due to the ocean. So basically you have the two main peaks, which are due to ocean gravity waves, and the long period noise, which is the seismic hem, which is due to the ocean infragravity waves. Infragravity waves are, while gravity waves, I should say first, are the waves that you see when you go to the beach and look at the ocean. So are basically ocean waves driven by wind and called gravity because they are restored by gravity force. Infragravity waves are long period, so the wavelength is much longer than the gravity waves and are generated by nonlinear coupling between gravity waves. This is really in short. So people have observed this because they also compare the ocean wave spectrum with the ambient noise spectrum and observed that indeed there are two peaks in the swells portion of the spectrum, and this spectrum resembles pretty much to what we observed from looking at the seismic waves and so the power spectral density of records. So let's have a look at the two main peaks. I will focus on those today. So the secondary microseismic, so roughly about between 1 and 2 seconds and 10 seconds, the generation theory was developed in the 50s and the 60s by Longe-Higgins and Hasselmann. And basically the generation process for this vibration of the Earth is about ocean waves interacting at the surface of the Earth, ocean gravity waves. When they are coming from opposite directions, as you can see in this cartoon, and they have a nearly similar frequency content, they generate at the second order approximation in the wave equations. So if you develop analytically the equations, you'll find that when you look in terms of amplitude squared, so the second order approximation, you'll find that there is a term coming up, which is a pressure term at the surface of the ocean, which doesn't depend on the ocean depth. So basically, this pressure is able to reach the seafloor, if you want. We can see like this, and generate the seismic wave field in the solid Earth. You can also see this as a pressure at the surface of the Earth or the ocean, which generates acoustic or P waves, so compressional waves in the ocean. And in turn, those are transmitted and also converted at the seafloors, as you can see here, multiple times when they are reflected, multiple times between the seafloor and the ocean surface, and generate S waves, P waves, and so the whole wave field. So this generation theory explains very well the Rayleigh wave content of secondary microseismic. And it doesn't explain, and I will very briefly talk about this at the end of my presentation, doesn't explain the generation of log waves, because the pressure source, in the absence of any roughnesses, so like a bathymetry or 3D structure, cannot generate any shear motion. So from this theory, you'll get just body waves and SP waves. Moving further in the spectrum of ambient noise, you have primary microseismic. And here you have a cartoon showing what's the generation theory developed mostly by Hasselmann in the 60s, and then extended by Ardoin et al. In 2015. So in that case, you are at much longer period. And so the ocean-wave interaction is not efficient anymore. What you have in terms of generation mechanism is another wave-wave interaction, but one of the waves is frozen. So basically you have an interaction between the ocean waves coming towards the coast and the frozen wave, which is the bathymetry. So a single wave arriving at the coast, interacting with the bathymetry, enhance the pressure when the water is shallow. As you can see here, the bottom pressure is negligible in deep water, as you expect from fluid dynamics. Basically, the particle motion decay exponentially with depth. You don't get anything at the seafloor from one single ocean wave in deep water, but you get a strong pressure close to the coast. And actually, with this reasoning and looking at the long wavelength pressure that you can get, this purple line here, you can actually relate the wavelength of this long wavelength pressure variation with the location, the exact position along the profile of the source. And so you can work out where the sources are. So now that I just gave you a brief overview of the generation of seismic ambient noise, we can talk about how we can monitor the environment. I will make the case of tropical cyclones using this signal. So as I said, we can monitor events in other systems, and tropical cyclones are particular atmospheric events in the sense that they are very strong and impact the ocean surface in a very significant way. You'll see here the wind field, and you see in the Western Pacific, and you see there are two strong typhoons going on. One is actually forming, is a tropical storm, or is not yet a big one. But then if you look at the ocean waves, you'll see that really this wind field impacts in a significant way the regions where the typhoons are. And if you look at the seismic records, this is an example in Japan, you'll see that actually the amplitude of the ambient noise increases a lot. So people in the years have been looking at the sources associated with events and both extratropical storms and tropical cyclones. Here on the left, you see a map showing one of the pioneer example of the so-called beamforming analysis for locating the sources of ambient noise. So basically in that case, what you need are stations close each other. And in that case, you can actually use the fact that waves, assuming waves arriving as plane waves, you can assume that this plane wave arrive at the array of stations all together at all stations, but you can use the difference in the phases for basically back projecting them and locating the sources of those events. On the right, you see the application, probably one of the first applications to a tropical cyclone. This was Hurricane Katrina, and you'll see that you get the patch where the hurricane is. So basically, motivated by those things that has been done, those studies that has been done over the years, we tried to locate the sources of one of the most long-lived typhoons in the history, and also one of the strongest is Typhoon Yok in 2006. So this occurred in the Western Pacific Ocean and lasted for about 20 days, which is really unusual. It's a lot of time for a tropical cyclone, and touched multiple times Category 5. This was studied pretty much in seismology because it's a very good case for studying the seismic signature. So what we did here was extended a technique developed mostly by Lise Ratailleux to this event, and we extended it in the sense that we trying to follow one phase, one seismic phase to try to reconstruct the entire track of the event. So we focused here on P waves. And what I'm going to show you is a movie showing observations from the space, from satellites of the typhoon in red. So you'll see a dot showing the typhoon track over time, and a circle like here around it, which shows the typhoon sites, which is defined in atmospheric science as a threshold in the wind field. Then I show you the results from seismology. So what you'll see is in green, results from seismology. So the maximum of the beam power, so what comes from the beamforming analysis following this specific phase. And you'll see with colors, instead of the beam power, so you'll get an appreciation of the dimension also of the source, because in this case, and this is different from earthquakes, we have an extended source. Ocean waves act over an extended region in the ocean. So I'm going to show you this movie. So as time goes, you see the typhoon going on, and you see that seismology, so the green dots at the beginning are really not great to locate the track. But after a while, you'll see that basically we're able to follow the events. And basically it's interesting, and this is basically in agreement with what has been theorized in the 50s. The seismic sources really follow the event. They are behind the event. And this is due to the fact that basically ocean waves for those specific objects which are moving and turning at the same time can interact only behind the event. And what you see at the end of my video is that basically we reconstructed the whole track basically using seismic waves, except for the beginning. And so what we thought to do was to basically measure the distance between every green dot, every red dot. So every seismic source and the atmospheric, the center basically, what is measured by satellites, so the eye of the event. And what we observe is that, of course, at the beginning, this distance is very large and is basically not related to the event itself. You've seen that those green dots at the beginning are really not related with the event, are just moving around. But then, and actually when you see there is a transition between the light blue, when it was the event was really weak, and then started to be strong, actually this distance start to be pretty constant. So you'll see that here, all over the duration of the event we analyzed, this distance, except for a few cases, it starts to be constant. And this distance is, we measured this as 34 knots winds. So basically correspond to this threshold in the wind speed. So this distance has been done considering and filtering the seismic data around 5-second period. Multiple papers in the literature have shown that this 5 seconds seems to be a very, very good frequency band, period band for studying those events. So we ask ourselves what happens at short and longer periods. So here you have the same plot, much more chaotic, but let's focus on the blue dots. So the short periods, you'll see that again, we have something not related with the event at the beginning of the atmospheric event. And then the blue dots, again, like the red dots, start to be pretty constant. So basically the source, both between 2 and 4 and 4 and 6, follows the event pretty closely and with the same distance from the event. But if you look at longer period, you see that basically you have sources all over the place up to the very end when they start to be very close and follow the event closely. So what happened at long period? And actually this is consistent with the literature in the sense that many people have tried to look at the long period signature of those events, a long period in the, I want to remind you, the secondary microseismic, so between 2 and 10 seconds. But they showed very few cases in which the sources could be seen. This is pretty much related to something that in the 60s, Olbrich and McCamey worked out. So for those events, in order to generate seismic signal, you need that the ocean waves the events, override its own generated waves. So you need at least that the group velocity of the ocean waves is equal to the speed of the event. If you develop this, you can work out a minimum period, so a cutoff period, which is the minimum period for the generation of seismic waves due to this ocean wave-wave interaction. And so we can compute this minimum period for our event. Here is the cutoff period as a function of time. So those black dots are show basically this minimum period over time, computed considering the speed of the event over time. And the background color represents the propagation speed that you actually have here. So what you can see is that the threshold is pretty low for all the duration of the event, and only at the very end it starts to be larger. What does it mean? It means that only when the event is at the very end of its life start to accelerate, and this actually happened because the event made the tropical extratropical transition, and so it accelerates its motion. You can see that in this case, you start to have a minimum period, which is pretty large. So this means that only at the end of the event, you could see long period waves, and going back, this is actually consistent with what we see. So the next step, which I want to discuss today, is that we are extended this study using multiple phases. As I told you, in this approach, you can get more about the methods already in the paper. Actually, we are following the different phases, and so we can actually study the different phases separately over time. And so we are now extending this to SV and SH waves. And SH waves is particularly important for the reason I told you before, because we don't know how shear waves generate from ambient noise. So now I move to the third part of my presentation, which is about modeling ambient noise. So this is, has been an effort that has been going on now for a while. Here you have two examples of pioneering works in which people try to use the findings and the models that we have in ocean sciences for studying microseismic. And here you have the one on the left by Kedar et al. And the one on the right is by Ardoin et al. Both used an ocean wave model called WaveWatch 3, which is a NOAA ocean wave model used by NOAA for doing ocean wave forecast and for studying basically the ocean in general, the surface of the ocean and the ocean surface waves. What have been done here, they used this ocean wave model to study the ocean wave interaction. And in the particular case on the right, Ardoin et al. 2011 basically added the possibility of having this ocean wave interaction close to the coast. So how this ocean wave model looks like nowadays. So here are 4 maps for secondary microseismic on the right. So those are the sources that we can compute using this ocean wave model, so between 2 and 10 seconds. And then on the right, you have the sources of primary microseismic. The first row shows you the situation in January, and the bottom row, the situation in July. So let's focus on secondary microseismic. You see that you have sources all over the place. And here the color scale, sorry, there is no color bar, but the color scale, so blue means really weak source and red means strong source. And you see that in January, the strongest sources are on the northern hemisphere, where it's winter, where storms are going on all the time, but you still see some sources on the southern hemisphere. On the contrary, in July, you really see there is a strong difference between north and south, and you have the strongest sources on the southern hemisphere. So the southern hemisphere is a bit special in the sense that you have the so-called storm track. So basically, the storms are not interrupted by continents. And so this is where the strongest sources on Earth, the strongest storms on Earth occur. And so basically, you have some sources going on all the time. For the primary microseismic, so we move on the right, the situation is different. You see, first of all, that you have a lot of white here. So basically, you have sources just along the coast and close to islands. So this is because the generation mechanism I described before. So you have the sources only shallow water. And you can see that comparing the two maps, you have a less seasonality than what you see for secondary microseismic, but you still have some. For example, looking at the North Atlantic Ocean, you see that there is a difference here. And the sources are much stronger during the local winter. So how we can use now those sources for basically making a model for ambient noise, like we do currently for earthquakes. To describe how this is possible, I use the normal mode formulation. So in general, a synthetic seismogram and the seismogram in general can be described as a sum of modes, so of vibrations of the earth. When there is an earthquake, you can decompose the motion of the earth in modes. So in single vibration, you can have the earth breathing like this and then having more complex shakings, and summing up all those, so basically having a Fourier expansion of the motion, you can retrieve the complete motion of the earth. So this is what goes here. So basically the sum all over the different components of the motions. Then the seismogram itself can be described as 3 terms. You need a receiver here, you need the source, and you need the propagation in between the receiver and the source. And so here the receiver is a seismometer that we have on Earth. For the propagation, we can use what we know about propagation of seismic waves in the Earth as we do for earthquakes. The source term needs to be different respect to earthquakes, the way we have to model earthquake signal. We need to adapt this framework for having a lot of sources all over the oceans. And so as you can see here, we have a grid of points, sources all over the oceans. And in each one of those point sources, we can actually use as the amplitude the one that we can get from the ocean wave model. So doing this, we can model, for example, primary microseismic, secondary microseismic. You have other techniques, for example, great circle approximation, which is the specific one I used here, but the concept is the same. You need the receiver, you need the source, and you need the propagation. You need actually many sources in this case. So using this, this framework for the sources, what we did was making a model for those 24 stations of the geoscope network that you see all over the world. So here you have each inset here shows you the power spectral density for one of those stations as a function of frequency. And the blue line represents data and the red line represents synthetics. And what you can see is that with this framework for the sources, we are able to get the first order approximation for the power spectral density, a good match between data and synthetics. And actually we can look at this over time. So this is the RMS of the displacement recorded at 4 stations of the 24 I showed you before. Data is in blue, synthetic is in red. And those stations are assorted as a function of latitude. So you have this station, which is farther north, and then you have this other one, which is more on the south, and so on, up to really the southern hemisphere. And what you can see is that, first of all, here is a zoom of 2 of those. First of all, you get a very good match between data and synthetics over time. We are even able to reproduce pretty well single peaks, which means that this framework for the sources is able to basically reproduce the sources of a single storm. And then what we observe is what we have seen also in the maps. There is some seasonality on the northern hemisphere. You see there is a strongest signal during winter and then is very low during summer and is less pronounced in the southern hemisphere. We can do the same for secondary microseismic. Those are 3 maps for the secondary microseismic sources for 3 hours observation and at 3 different frequencies, so, or periods. This is 4 seconds, 6 seconds, 8 seconds. You can see those maps are different. So these sources are not just time, space dependent, but also frequency dependent. So we need to account for this as well when we do a modeling of the seismic vibrations due to ocean storms. And so here is an example for the vertical component data, blue versus synthetic in the secondary microseismic band. So before we were modeling this band here, now we are modeling this one for 3 stations. This is in Africa, this is in France and Europe, and this is in Australia. And it's nice to see that those 3 stations are basically, this one is in the middle of the continent, this one is not that far away from the ocean, and this one is actually close to the ocean. And you can see the same in the seismic data. You can see that the amplitude of both the synthetics and data and synthetics is increasing, moving from left to right, meaning approaching the ocean. So those 3 power spectral densities and the ones I showed before for primary microseismic are all for the vertical components. So what happens when we try to look at the horizontal components? It happens that we don't get a good match. We get the gap between the synthetic power spectral density and the data. And this is related to what I told you at the very beginning. This generation theory developed in the 60s can explain the Rayleigh wave content, but cannot explain the lobe wave content. And on the horizontal component, there have been some evidence, actually several evidence, of the presence of lobe waves. Here on the bottom, you have the power spectral density acceleration spectral amplitude of the vertical component and also the Rayleigh wave component of the horizontal components of the records and the lobe wave part of the horizontal components of the record, which is this red line here. This was possible using basically seismic stations, but also some new instruments which measure the rotational, basically the rotation and the rotation rate of the ground, of the displacement of the ground. So as I told you, this mechanism, so a vertical force, as you can see in this schematic representation, can only generate Rayleigh wave. You don't get any lobe waves. To get some lobe waves, you need some horizontal forces. And people over the years have tried to basically give an explanation for what we observed. This chart shows you, this table shows you about 100 years of observations in seismology, where you can actually, there are more which are not in this table, that hearse back really at the beginning of the 20th century, where people observed those lobe waves, but they couldn't explain how those, why those lobe waves were present in the data. And so there are two possible explanation, two possible hypotheses for this. One is that this vertical force, as you can see here, in the presence of an inclined surface below the source, so the bathymetry, for example, can generate some horizontal forces, or for better saying, parallel to the seafloor, and also some perpendicular forces. So basically can generate a force splitting at the seafloor. This horizontal force could be responsible for the generation of lobe waves. On the other end, another possibility is that 3D structure through some scattering effect, but also focusing on the focusing effect, conversion between modes could actually lead to some energy in the lobe wave part of the seismic records. So I just want to show you this slide about this. We are working on that. We are making some models using maps of the sources of ambient noise, as I show you here, using a realistic 3D earth structure and topography, and we are making simulations down to about 4 seconds. And to basically try to solve this mystery in seismology and try to understand where those lobe waves could actually come from. So with this, I want to basically give you 4 take-home messages, mostly 3, and the 4th one as well. So the first one is that nowadays, thanks to the decades of study that have been done on the generation of secondary microseismic, primary microseismic, and in general background vibration of the earth, we understood that this is not noise. This is really a signal that comes from the ocean, and we now know the major aspect of its generation process. The second take-home message is that we can locate the sources both with models and observations, and we can actually relate those sources with the events that generates those sources. So in the atmosphere and in the ocean. The third take-home message is that we have now, thanks to the advancement in computational seismology, make models, so make predictions for the ambient noise, power spectral density, and the amplitude of the ambient noise. And we can do this using simple models. So we can do this using very complex models in seismology. And the fourth take-home message I want to give you is that we are a big topic in seismology, and we are approaching some conclusions for this is where the shear motions generate, and we are going towards this. So all this framework is useful in the sense that, as I said at the very beginning, allows us to study other systems, so that, and notably the atmosphere and the ocean, using seismology. And I want to point out that in seismology we have digital, very good digital data since the 60s. And so the possibility that we have to basically extend back our knowledge of those events back in time is pretty high. The 60s is when basically the satellite era started, with just a few satellites going on at the time. And so basically what we can do with this is to bring together atmospheric science, oceanography, and seismology, and work at the interface of those different sciences. Then the third future perspective for this is really to image the Earth structure using ambient noise, but using also what we know about the physics of ambient noise generation. As I said, and I told you at the beginning, at the moment we are making maps of the Earth using ambient noise, cross-correlating those signals. But this framework assumes that you have sources of ambient noise all over the places in a uniform distribution. So basically we're not accounting for the physics of the generation of ambient noise, which instead tells us that the sources are seasonal and the sources occurred in specific regions at the time. So with this, I wanna leave you with this slide where I want to thank my collaborators all over the years and the people I had the pleasure to work with. Thank you.
Great, thank you, Lucia, very nice talk. And I think we're ready to take questions from the audience. Please make sure to unmute your microphone before you speak.
So Duncan Agnew, I have, first of all, it's pleasant to see Dick Haubrick's stuff is still remembered. My question, just to be awkward, is any thoughts about the 26-second microseism peak?
Yeah, this is a good question. This is another mystery in the ambient noise community. Well, there are so far just a few studies, and it seems that a 26-second peak, so for those who are not familiar, it has been observed in a few papers that at 20-second period, there is another small peak. And people tried, like the secondary microseismic and the primary, but very narrow, around 26 seconds. So people tried to locate this and found that it should come from the Gulf of Guinea. So basically that part of the Western Africa. So we haven't seen, let's say I haven't studied at all this peak. The generation mechanism, at least from what the literature said, should be different than primary and secondary, and the seismology community didn't come up with an explanation so far. So no, I don't know.
Hello, this is Mariana Eneva. I have a question about, I read recently that seismic noise in general, I guess not the ocean related, but human activity has gone pretty down because of the pandemic. So is there anything that you observed is seen better now when this human activity related seismic noise is more quiet?
So this is a good question, yes. So in general, I show you in one slide that at high frequency, you have the influence of human activity. So yes, seismometers all over the world are recording some very low vibrations at those frequencies due to basically the stay-at-home condition. So I know there are several studies and going on at the moment trying to see if there is something that actually comes up from the this very low background. In particular here at Stanford, and in particular Nate Lindsay, which is a postdoc here in geophysics, is working with some fiber optic data. We have a fiber optic line going on here on campus, and we are observing, as all over the world, a very low noise signal. What we are trying to do is actually to see if we can say something more about traffic using this information.
Okay, actually, I have a question. Can you tell us more about how the researchers came up with the the source distribution and their amplitudes of the microseismic, the second and primary microseismism from the oceanography models?
Yes, sure. So basically, this is really, they really applied the physics of the generation that Longe-Higgins and Hasselmann work out analytically. So if you check those papers in the 50s and in the 60s, those are analytic papers where they worked out all the generation theory. So you have really equations. Those big ocean wave models can compute many other things. But you can also add this physics. So basically you can add as a possible source the interaction between ocean waves. So what they did was to code and add in those models this mechanism as well. And then we could observe, we could see the models, the synthetic sources.
So as shown in those figures, the sources of the secondary microseismism are mostly, so they are distributed in the ocean, whereas the primary ones are concentrated on the coast. Is that because the generation mechanism of primary seismism, microseismism, is related to the interaction between ocean waves and the coast?
Yes, so it's basically related to the interaction between ocean waves and the sea floor, and this can happen only in shallow water.
Oh, I see.
So you can have sources close to the coast, but if you remember my slide, you also have some sources associated to islands, where basically—
Yeah, I saw those, like in Hawaii and—
like here,
Okay, great.
So you need the shallow water condition, basically.
But secondary microseismism can be generated in open ocean.
For secondary microseismic is really an interaction between ocean waves that happens at the surface of the ocean. So those ocean waves for secondary microseismic have a wavelength of tenths up to hundreds of meters. So also in deep water, this is really the first layer on top of the ocean. And so it can happen everywhere.
Okay, great. So Ignacio has a question. Ignacio?
Thank you, Dianse. Hi, Lucia. Thank you very much for the presentation.
Hi.
Very nice.
Thank you.
I know what you are dealing with the paper, with the thesis of Longe-Higgins, because I have been trying to read it and try to extract some things for some studies in power spectral density, and it's very tough. Like 2 weeks to understand one line.
Oh wow! It was more than 2 weeks to formulate one line.
Yeah, but very, very hard. Yeah, but very useful. But I have a question related with that question that Duncan was saying about this particular period. I'm thinking about what is going on with the interaction between the coast and these waves, because, for example, first of all, you have breaking very close to the shore. I guess that contributes with very high frequency in this noise, but also you have other processes close to the coast. For example, as in the Gulf, in gulfs or continental shelf, you should expect to have some resonance of long waves, infragravity waves, or even tides, which maybe can have a significant contribution to your long periods in the noise that you are observing. And for example, I started to remember when you were talking about this period. For example, in Chile, because I'm from Chile, I was sailing there. I have a friend, and we were going out to sail. And there are very famous gulfs in which the sea states are very tough. And basically, in order to understand the wave field in those gulfs, basically you have to go to very sophisticated model in order to understand wave propagation. And of course, you cannot use shallow water theory in those regions. So I'm thinking that maybe if if a better model in order to understand the wave propagation in these kind of gulfs and continental shelf maybe can give an answer about what is going on with long periods in the seismic noise, rather than apply shallow water equations or shallow wave theory.
So, so if I understood well the question, so basically you are asking why, if it is possible that one mechanism can contribute also in the other frequency band. So if you can have ocean wave interaction having some effects in the primary microseismic and vice versa, the direct coupling in the other bands. So unfortunately, I don't have the figure here, but you can check the paper by Fabrice Ardouin, 2015 GRL paper. Basically, what we did was to verify both mechanisms. So in that paper, we call the primary mechanism and secondary mechanism. And we tried to see what's their effect over the primary and secondary microseismic bands. And you'll see that basically the primary mechanism is only able to explain the data in the primary microseismic band. Otherwise, it's very low. Its contribution is very, very small. And the vice versa, the secondary mechanism is only able to explain the data in that band. And the contribution of this mechanism in the other band is very low. So regarding very sophisticated, let's say, and complex ocean activity, like, for example, turbulence, Hasselmann in 1963 in his paper actually verified, if I don't remember well, it's really at the end of the paper, he verified that turbulence should not affect, in any case, the generation of seismic waves. But of course, that's the state of the art. And that's the beauty of science. So maybe in a few years, we will discover that with more sophisticated models, we see some other effects. But that's the current state of the art.
Wonderful. Thank you, Lucia.
Thanks for your question.
Okay, and Ruijun has a question.
Yes.
Hey, Ruijun.
Hi, hello. Thanks, Lucia.
Hi.
Hi. I have a question about your future work. You put in the future work one is you can apply this knowledge to the cost correlation things about ambient noise cost correlation. So I had experiences in doing ambient noise cross correlation, and one of the problems I faced was because the uneven distribution of the source direction that results in inaccurate cost correlation function, which we measure is not a true phase arrival time, it's actually the apparent phase. Sure. So I wonder, how can we correct these things if it's possible, as long as we know about the source direction or the source configuration? How can we do for the correction? So
that's a good question. So what I was trying basically to convey is that we could use something like we do for earthquake, but also for ambient noise. So we could really do a comparison between a model which takes into account the sources and the data. So not just correct the cross correlation you observed by the sources. That's maybe possible in some other ways. But what I'm thinking here is really to do a simulation, a full wave field simulation of ambient noise, considering all the sources, having this quasi-random synthetic, quasi-random vibration of the Earth, and then compare this in terms of power spectral density, in terms of correlation between stations. There are many ways of comparing data and synthetics with the data. So it's more an earthquake-like approach than the classical ambient noise approach.
I see. Okay, thank you.
You're welcome. Thank you.
All right, any more questions?
Can I ask one question? Hi, I'm Haejong from Japan.
Hi.
I read your paper in the typhoon tracking one, and I was curious whether the secondary microseism, the long period secondary microseism energy is always low until it meets certain condition, you said that like in the beamforming analysis, you could not have a good tracking using those 6 to 9 seconds. And does that mean the energy itself stays low for all the periods of the typhoon?
Yes, so basically the typhoons are particular objects in the sense that atmospheric phenomena, in the sense that they move, but they also turn over time. So they are turning anti-clockwise and moving at the same time. So basically what happened in terms of ocean waves is that at a certain time you have, so ocean waves are moving in the same direction of the wind. So at a certain moment you have ocean waves going, for example, in one direction, and then at the moment later, the typhoon just turns, and so the ocean waves are going in the opposite direction. So at time 2, you will get some ocean wave interaction on the tail of the event. So I don't know if I was able to explain well this. So you can check the Longhagen's paper 9052. He explained very well how this happens. So in terms of ocean wave interaction, in order to have this specific condition, what you need is that your object that is moving and turning at the same time is moving basically faster than the group velocity of ocean waves. In that case, you can have the interaction on the tail because you always leave behind the ocean waves. So of course, ocean waves are dispersive, and so this condition depends on the period. So this is basically what it is in this slide here. So if you impose this condition, so which is the boundary between you don't have a wave interaction, you have a wave interaction. If you impose this and you use, this is the deep water approximation group velocity for ocean waves. If you impose this, you'll find a threshold in the period for ocean waves and then for seismic waves, because we know that for secondary microseismic, the secondary microseismic occur at half of the period of ocean waves. So if you have ocean waves at 14-second period, you'll get ambient noise at 7-second period. So you can actually relate the ocean wave period to the seismic period. And so you can work out this threshold in the period, which depends on the speed of the event. So if it goes very fast, if V is large, you'll get this minimum period, which is pretty large. If it goes very slowly, then you'll get a very low minimum period. So this means that only when it goes fast, you can get some interaction of ocean waves at long period, which will generate the long period ambient noise.
Okay, thank you.
Thank you.
All right, any more questions? All right, I think maybe it's time for us to wrap up. Thank you very much, Lucia.
Thank you.
And very nice talk. And it's very nice to have this format of seminars to let people stay connected during this strange time of extreme isolations. So we'll probably meet again next week with our next seminar speaker. And with this, thank you everyone for attending, and hope you will stay safe while being productive at home. Thank you.
Thank you. Bye.
Bye.